talks. There's one which I've just mentioned. This is a bad one. It has the right shape. The shape can be deceptive. Topic number one, formality over Q is actually equivalent to formality over any field of characteristic 0, well, in particular over R or C. And basically, it's not very difficult. If we're allowed to assume a few things about arithmetic groups and algebraic groups over Q.
Maybe I can. I think it's interesting for any K, yeah?
Well, for any K, but we're mainly interested in the case K equal R, K equal C. Well, sometimes there are manifolds which are manifestly formal over C. For example, compact Kähler manifolds. On the other hand, we also have non-compact examples as well. For example, the famous example of configuration spaces of points in R2. So if we have the space of ordered configurations of endpoints in R2, then there is an explicit algebra well, let me write C instead of R2. And we have an explicit model, and the model is generated as an algebra by the forms d log zi minus zj for I different from j, and those satisfy Arnold's relations, which are famous because they come up in many other examples as well. Anyhow, the space is manifestly formal over C, but as you can see, there is a log here and as a result, these forms are not Q polynomial in any meaningful way. Okay, so solver. Okay, but this will require some work. Okay, you're in. Great. So.
I think it's a long lasting question, because we have a lot of seminars before.
Yes, well, it would make sense to cover compact Kähler manifolds and C formality before that.
Because maybe I want to understand proof which use algebraic proofs.
Yes, so as I said, there are two proofs. There is one by Sullivan which works for which works if we consider nilpotent spaces, and it sort of works for arbitrary spaces, but it's more complicated because instead of algebraic groups, which are well, sort of tractable, we need to consider pro-algebraic groups, which are also tractable but more complicated. Anyhow, so at least. At least for nilpotent spaces of finite type. So that all groups are genuine algebraic groups. Okay, so there's a simpler topic. Which is modeling vibrations. I've decided to have someone other than me speak about vibrations, but we will see the main idea hopefully today. And topic number 3. Is modeling loop spaces and the Whitehead product. Well, there's a more or less straightforward way to construct a model for a loop space, starting from a model of the given simply connected space. And a loop space is an H space. So it has a product. And using this product, one can recover the Whitehead product on the homotopy groups tensor Q. So we all know that there is a mysterious Whitehead product on on the homotopy groups. And it's a natural question whether or not this product is computable by looking at the Sullivan model of the space. The answer is yes. And to do this, well, the easiest way would be to first model the loop space but not just model. We need to model the multiplication as well. Okay, are there any volunteers for either of these?
I can try the second topic.
Which one?
Second topic.
Okay, so I think yes. Very well. What's your name? Say again.
Maybe I can write for you.
Jeeping.
Yeah.
Okay, very well. I think this topic looks like the right topic for you. Good. So you're Andre. Very well. I think this is basically this particular topic in particular is covered in the book by Felix Halperin and Thomas, and the presentation they give is I think straightforward and does not use any difficult calculations. I think one seminar should be enough to cover this. Yes. Yes. Yes, same applies. The same applies to the second topic, but in this particular case, the way Felix Halperin and Thomas cover this particular topic is a bit too technical, and it's not always clear what they're trying to do. For the second topic, we probably need to talk on Zoom or in person, and I will try to explain how it works. Okay, so it looks like everyone present has already something to think about. Okay, so let's.
Sorry, when we start Syria of these topics on the next seminar?
Yes, I gather from Alexei and Mikhail that both of them will be ready to speak next week. Is this realistic?
Next week, one where
Yes, the preliminary plan is one half for Alexei and the second half for Mikhail. Okay, so Andrei, have a look at the paper. Does it make any sense? То есть к следующему разу ничего не нужно, но значит, через раз хотелось бы поговорить про... нет, через раз будет, значит, будет это самое...
Нет, там, кажется, статистика такая, что на следующий раз кто-то из...
Значит, через раз, по идее, будет Аршак. Значит, про... Да, значит, рассказывать будет он про Бусфилда. Ну, итого, значит, ну, такой предварительный план, значит, сделать про Келлера либо в следующий раз, либо, значит, либо через раз, либо через 2 раза. Значит, ну, давайте скажем, что план А через раз, но может быть через 2 раза. Значит, ну, вот те куски, про которые, значит, про которые я написал, это, по сути дела, просто линейная алгебра. Значит, мы можем, там, как черный ящик, использовать то, что там все определения келлеровости эквивалентны вот тому, который нам удалось сделать из цели. Okay. The talks start next week, and then we'll basically see how it goes. Okay, so let's try to remember what we started last week. We have 2 categories. We consider, on the one hand, space is localized in maps which induce isomorphisms of the rational homotopy groups, and on the other hand, we have. Let me write it here. So I have this category. And I have a similar category for CDJs, and actually, before I write the adjunctions, I need so okay, we want to we want to prove that the category of spaces localized at blah 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 is equivalent to the category of CDJs localized at blah blah blah. To do this, we construct functors, and unfortunately, we need to include simplicial sets in the picture. I don't know how to do this without simplicial sets. No. Okay. I will try to write the right adjoints below and the left adjoints above. So we have the functor APL and the functor of the geometric realization. I don't remember whether or not they were constructed last week, but we will see the construction in a few minutes anyway. And there is the functor which takes a space into a singular simplicial set, and the geometric realization functor from simplicial sets to spaces. Okay, we will assume that the top two, the first two functors and the first two functors are something we will sweep under the carpet straight away. Let's assume that those two are adjoint, moreover, Gwillen adjoint, and the resulting map of the localized categories is an equivalence. If I start, if what I say stops making sense, please let me know. If none of it made sense to begin with, the same. Please let me know. Okay, to the cochains are contravariant. So in order to talk about a jointness, I need one of these categories to be replaced with a top. Well, I want to replace this one with the opposite category.
Can you recall the definition of clear joint functors?
Well, so suppose we have C suppose we have two model categories, C and D, and two joint functors from C to D, and there are several equivalent ways to define Quillen adjunctions. Okay, let me give two versions, but there are more, and we will learn those next week from Alexei's talk. So version 1, L, the left adjoint, preserves cofibrations. And cyclic cofibrations.
Left joints and cofibrations, two configurations.
Yes.
Configurations in C, two configurations in D.
Yes, and the same for cyclic cofibrations. B R preserves yes, fibrations. And cyclic fibrations. And there are several several more ways to state the conditions.
Maybe we should note cyclic configuration or cyclic configuration. Or we can say only this definition only about separations and configurations. Without cyclic.
Yes, there is a way to state this using just fibrations and just cofibrations, but in practice the versions that will be the most useful, at least for us today, are the ones that include just one of the functors. Normally, well, not normally. often. One of the functors is relatively easy and the other one is complicated. So in this case, we just look at the easy functor and see whether or not it preserves what we wanted to preserve. In general, and this is important, none of the functors preserves weak equivalences. If the functors did preserve weak equivalences, then the construction of the derived functors would be much more straightforward. Well, basically, we already see something like this in classical homological algebra. We have the tensor product functor, and unfortunately, it doesn't preserve quasi-isomorphisms. So to define the functor between the localized categories, which is the same as the derived categories, we need to take flat resolutions, and this basically generalizes the same philosophy for arbitrary model categories. Okay, so let's define those two functors. Let's recall that we have defined differential forms with piecewise. If we have the standard simplex, then we have polynomial forms on it with rational coefficients. Very well. Now, if I map delta n into delta m in a piecewise linear way, the forms go to the forms. So using this, we can construct a simplicial object in the category of CDGAs, and I denote the resulting thing by APL. Does this definition make any sense? And by the way, does the word simplicial make any sense? what does the word simplicial mean? Okay, so
And what is simplicial?
so what's the difference?
I don't know, and I asked you about it.
Oh, you're okay. So the word simplicial does not make sense. So we need to explain what the word simplicial means. Okay, so uh, to begin with, we define the category delta. There are two equivalent ways to define this category. Firstly, we can take all finite non-empty sets, ordered sets. And non-decreasing maps between them. Equivalently, we can take the sets of the form 0, 1, 2, 3, etc. n for all n greater than 0, greater than or equal 0. And again, we consider non-decreasing maps. Now, a simplicial object in the category C is a contravariant functor from the category delta to C, or in other words, a covariant functor from delta op to C. Cos or co-simplicial objects, don't know which one's the right one, are also useful.
Simplicial objects, it's function from C to delta.
No.
From delta to C.
Yes.
It's not true. It isn't true. Whole, I think.
So co means we remove the op. And there is there is a good there is a good source on this theory. Let me try to remember the name of the author. Okay, so everyone has a tablet. Try, please try looking for Friedman with F-R-I-E. Simplicial sets, and see what you find. And then please tell. Say again. Oh yes, an elementary. So, but the spelling is correct.
Yes.
So it's G. Friedman, elementary, illustrated.
This is a good way to understand simplicial sets.
Yes. An elementary illustrated introduction to simplicial sets. Is this correct, Alexei? Say again? Okay, so for those of you who haven't seen simplicial sets yet, this is the introduction I would recommend. And there's, well, there are other references, but I think as a first approximation, this one would suffice. Okay, so this is just the definition, and it doesn't really give one any intuition about how simplicial sets behave. And very vaguely, simplicial sets are something like topological spaces, but they are combinatorial, for what it's worth. Okay, so we using this definition, we can define. There's just one. Just one thing which I probably need to mention as all maps can be written as products of the maps of the following type. We have delta I. Okay, let me write. From n to n plus 1, which omits the ith element, and as I going in the opposite direction, it doubles the ith element, or repeats. Okay, now let's see. Okay, now so to construct a simplicial CDJ, we need to construct for each n greater than or equal 0 a regular CDJ, and for each of those maps, we need to construct a CDJ map which goes in the opposite direction. Do we want to spell it out on the blackboard? Okay, so for each n greater than or equal 0, I define the nth component of APL. And the nth component should be just a CDJ. Well, I take the cube polynomial forms on the standard syntax. Now, for each of those maps, I need to define a map between the components of APL. But since I want a simplicial algebra, the maps will go in the opposite direction. This thing is the cube polynomial forms on delta n plus 1. I have a map of simplices delta n plus 1, which is affine, which takes vertices to vertices, and which in an increasing way, and which misses the ith vertex. So basically, on the level of vertices, I take precisely this map. So let me just vertices to vertices and delta I. And the map of the set of the sets of the vertices is just delta I. Okay. Well, similarly for SI. I take this time the map will go from from the nth component to the n plus first component, and it will be induced by the map of delta n to delta n plus 1 to delta n, which is affine, takes vertices to vertices, and on the level of vertices, it's given by SI. Okay. Are there any more questions about this construction? Good. Now we are ready to try and define the functors. Okay, so let me raise.
Excuse me, so what is this simplicial
A simplicial something is a simplicial object in the category of somethings. So we've just actually defined this APL explicitly. Firstly, I want to define the APL functor from simplicial sets to CDJs. So suppose I have I have a simplicial set. APL is the way we defined it. APL is a simplicial CDGA. So in particular, it's a simplicial set. So we can take maps of simplicial sets from K to APL. More and well, of course we can, but what do we get? Let's let's do this more explicitly. We consider the set of the set of sequences so for each for each I, the ith element should be just a map of sets from Ki to APL I. Plus some compatibility conditions which come from the fact that this is not just a collection of maps. It's a natural transformation of the two functors. Now the product suppose we have two maps, Fi Gi from Ki to APL I. Now these are this time these are just maps of sets, and we can multiply them pointwise. These are maps of sets which take values in a CDGA. Well, we just multiply them pointwise, and we get another map with values in the same CDGA. Well, for those of you who were wondering about why this works, the answer is any set is well, sets are not monoids in any meaningful way. Well, every set can be made into a monoid, but maps of sets do not necessarily preserve the structure of a monoid. But every set is a comonoid with respect to the natural monoidal structure on sets, which is just a Cartesian product. So every set, in other words, can be viewed as a co-algebra. And the maps from a co-algebra to an algebra form an algebra. And similarly, maps from an algebra to a co-algebra form a co-algebra. Okay, so if this explanation doesn't really explain anything, let's just think of this as pointwise multiplication of maps into an algebra. Okay, so and similarly, if we have two sequences, we just take the component-wise product. Okay. Now, are there any questions about this definition? Now we need to construct the joint functor and the construction is very similar. So this was APL. Starting from a simplicial set, I get a CDJ. Now, I want to go in the opposite direction. Starting from a CDJ, I want to construct a simplicial set. And now I take maps again into APL, but this time I consider APL. I consider CDGA maps into APL. What does this mean? Well, for every n, I take all CDGA maps from A to APL n.
I'm sorry, but wrong. We can use sets. It's objects in the sets. It's functors from delta op to set. And why we can construct this space of joint functors with forgot functor. We can forgot algebra structure on CDGA and we take simplest sets. APL it's simplicial CDGA, it's simplicial object in CDGA. It's object from delta op to CDGA. Yeah.
Yes.
And where we can use I think foreign functor from CDGA to set and composition of functor from APL to set. It's I think simplicial sets. Why didn't
So я не понял абсолютно ничего.
Ну, у нас есть, хорошо, ладно. Но у нас же есть функтор из алгебры, ну, CDGA, множество, забывающее просто.
Да.
Что такое симплекциальное множество? Это функтор из дельта op в сет.
Да, хорошо.
Соответственно, мы можем сконструировать по... мы это делаем, наверное, да, сейчас? То есть мы сейчас как бы учимся конструировать функтор из... Нет, сейчас мы... Да, сейчас мы конструируем функтор CDGA в S-sets. Почему мы не можем сделать так? Вот у нас есть дельта op, и у нас есть функтор из дельта op в CDGA. Это ровно значит, что эти Q, вот эти от КЦ PL, они симплекциальный объект в коммутативном дифференциальном Ливером алгебре. Почему мы не можем взять композицию с забывающим функтором?
Значит, итого, вы хотите построить значит, какой-то из этих функторов.
У нас просто есть очень простое описание для сопряженных функторов забываемых. Ну, сопряжение забываемых, там взять...
Значит, что такое забывание? Значит, есть там есть правые сопряженные функторы, но есть забывающие функторы. Но, значит, забывающие они, как правило, правые сопряженные, но значит, понятия вот, значит, общего понятия забывающего функтора нет.
Ну, нет, значит, есть забывающий функтор и CDGA в множестве. Просто будем рассматривать как бы алгебру как множество.
Так.
Это здесь есть.
Так.
Почему это не конструировать нужны нам какие-то функторы? Нам же без разницы, какие это функторы. Нам нужно просто, чтобы они были какие-то сопряженные там.
Да, значит, того идея взять алгебру, значит, и рассмотреть ее как множество. Да, но потом, да, но нам хочется симплициальное множество.
Да, у нас же есть как бы функтор из дельта op в алгебре, и мы берем его композицию забывающую. Она уже может быть никак не сопряжена ни к чему.
Сейчас, значит...
Функтор это конкретный вот это APL. Нам нужно
Так, хорошо, значит, разобрались. Хорошо, окей, ничего страшного. Very well. So we have two CDGAs, maps from CDGA maps from one to the other are just a set. They're not monoid or co-monoid, or they basically do not have any meaningful structure. Well, they do, but basically same as in algebraic geometry. Maps from one commutative algebra to another one is maps of commutative algebras A to B are spec B valued points of spec A. What is it? Well, it's complicated. Anyhow, so this is a map, this is a set, and then we, when we take those in for all n, we have a simplicial set. Now we need to see that we need to see that the functors are adjoint. Let's try to do this. Actually, there's one important thing which I forgot. The functors should be from simplicial sets to CDJ op, and from CDJ op to simplicial sets. So we want to prove that the APL functor is left adjoint to the other functor. Well, let's try to do this. So suppose I have a K. A simplicial set. And I have an A, a CDG. I need to prove that the result is the same as simplicial set K. So this is what I need to prove. Well, let me rewrite the left-hand side as CDGA, A, APL of K. Well, this is just by definition. And now let's remember the definition of APL of K. Well, we have this this by definition. Let's similarly rewrite the right-hand side. And let's remember the definition of the geometric realization of A. So K CDJ APL. Okay, so the formulas look very much the same, but still not quite. Let's have a break, and in the meantime, let's think how to identify these two objects. And once we've done that, we will have shown that the functors we constructed are in fact adjoint. Are there any questions? вопрос ко всем присутствующим. Есть ли что-нибудь на YouTube из этих занятий? Так, хорошо. Тогда более конкретный вопрос. Значит, что есть и что нет. В общем, просьба разобраться с тем, что выложено, что не выложено, и, соответственно, если что-то не выложено, я подозреваю, что так оно и есть, то тогда я уже буду говорить с Гошей. Но к чему это приведет, сложно сказать, но, по крайней мере, я пытаюсь. Итого вопрос, что выложено, что не выложено, и второй интереснее, чем первый. Ну, это, конечно, хорошо, что последний есть, но, в общем, просьба прислать список тех занятий, которых нет в YouTube. Ну, и я, соответственно, это, с этим попробую пнуть Гошу, и, мы посмотрим, чем он закончится. Ну, какой-то эффект есть все-таки. Он не стопроцентный, но он есть. Okay. Well, there's just one thing that, which I need to which I didn't say about this construction, and I need to state it. This is supposed to be a graded object. So I need to specify the grading, and if I take a fixed grading, let's say P, then each degree P component of APL is a simplicial vector space. Well, then here I take all maps of sets, but these become a vector space because the target is a vector space. So with this extra remark, we get a genuine CDJ. Now, back to where we left off before the break. We have two things. Those things are just sets, and we want to identify those. How do we go about this? well, we would like to view both these as maps of A times K to APL. Well, what does map in quotation mark mean? Well, this means the following thing. It's the set of all collections Fn from A cross Kn to APL n such that well, firstly, we can view A cross K as a simplicial set. If we already have a simplicial set and times it with another set and declare all structure maps to be what they were times the identity of the other set, we get a simplicial set. So firstly, we require this collection should satisfy the simplicial identities, meaning it should commute with SIs and delta Is. And secondly, for every fixed element of K, let's call it X, the map we get a map from A to APL, and this should be a CDGA map. And my claim is unwinding the definitions. We get this thing on the one hand and this thing on the other, which shows that the two functors are adjoined. Are there any questions, comments, remarks, objections, criticism? Okay, so we have constructed two functors, and we have checked that the two functors are adjoined. Now we want to show that they're not just adjoined, they're equivalent adjoined. APL. Going from simplicial sets to CDJs. Is joined to the geometric realization. Very well. Now we need to show that the functors are equivalent joint, and in order to do this, we need a model structure on both sides. And for CDJs, we already saw that assuming some theorems, which Misha will talk about next week, there is a model structure on CDJs which is obtained by transferring the injective model structure on complexes. Okay, but what about simplicial sets? Do they have a model structure? Well, they do. And I don't want to say much about the standard model structure on simplicial sets because at the moment I only want to show that the two functors are equivalent joined. Okay, so we have the there's one important thing. Op. So the easiest way to proceed would be to remark that APL takes component-wise inclusions, which are the cofibrations to two component-wise surjective maps of CDJs, which are the vibrations for CDJs. So it so happens that for simplicial sets, it's easy to describe co-vibrations, and the vibrations are slightly trickier. They're the convibrations. Don't want to talk about this. And for CDJs, it's easy to describe the vibrations. The vibrations are just the component-wise surjective maps. And my claim, which needs to be checked, but it's not massively difficult. APL takes co-vibrations to vibrations, which means to co-vibrations in the opposite category. To co-vibrations. And another thing, APL preserves weak equivalences. Which is essentially Durham's theorem. It's very rare that an interesting functor preserves weak equivalences, but it sometimes happens. So the adjunction is equivalent adjunction. And now we want to understand whether or not it's equivalent equivalence. Equivalent equivalence. I should practice it. And the answer is no. But in general, let's let's suppose we have two adjoint functors. The categories C and D are not necessarily equivalent. But, nevertheless, we do get an equivalence between a certain full subcategory of C and full subcategory of D. So if we have two adjoint functors, these induce these induce an equivalence between two subcategories. Which ones? Well, let's remember that if we have a pair of adjoint functors, we have two natural transformations, the unit and the co-unit. Well, let's try to remember where these transformations go from. For example, the unit. It's a transformation between which functors? Say again? LR to unit. LR in which order? Okay, firstly L, then R. Okay, and so Salva claims that we have this natural transformation, which would be the identity of C. Now let's have a look and see if we agree. Нет ли здесь обмана? Нет, ну там в Википедии там каждый может найти. Значит, как это понять, если вдруг Википедия исчезла? Ну, давайте вспомним. So let's try to figure it out. Okay, so let's have a look. So we have a left adjoint and the right adjoint. So D Lx y is the same as C x r y. Okay, so let's take y equal L. So this should be true for every x and c and y and d. Let me take y equal Lx. So the Lx. Let me not bother with those morphisms. C X R Lx. So by taking the identity here, we get a map from X to RLX. So it's the other way around. And similarly, this time we need to take x equal ry, and we get the co-unit which goes in the other direction. Okay, does everyone agree? And by the way, every junction gives one a monad. Does the word monad ring a bell? Okay, well, then we'll not say anything. We won't say any more about it. But monads are important. Especially in topology. Anyhow, every junction gives us a monad and a co-monad, and but there could be several junctions which give the same monad. Okay. Now. So let's take C prime to be the full subcategory of all X and C, such that the unit is an isomorphism, and delta prime, d prime, again to be the full subcategory, such that the co-unit, let's call this eta, and when we well, there are two claims. Firstly, if we restrict the functor L to C prime, we end up in D prime, and vice versa. If we restrict R to D prime, we end up in C prime, and the resulting functors are in equivalence. Which is useful. Which is useful in our case. Are there any questions? So every junction gives us an equivalence between something and something. And neither of the two somethings needs to be the whole category, but it's a full subcategory. So I want to describe a subcategory of simplicial sets, which a subcategory of simplicial sets on which the derived unit. Yes, I want to take the unit. Yes, I want a subcategory of simplicial sets on which the derived unit is an isomorphism. But what does the word derived unit mean? Well, let's see. Suppose we have a equivalent junction. The other way around. As we will see next week in Alexei's talk, if we have equivalent junction, we always, not necessarily equivalent equivalence, we get a pair of adjoint functors between the homotopy categories, or which is the same between the localized categories. And now the question is, how do I calculate those functors? Well, well, let's start with the left adjoint. Let me explain how to calculate those functors and objects. And I start with a cofibrant or cofibrant replacement. So suppose I have an X in C. I take the cofibrant replacement. Now, does the expression cofibrant replacement make any sense? well, I think Misha and Alexei already know what this means, and the rest, not really. Okay, so let me say something about it. So we want to so we have a map, a unique map from the initial object to X. By one of the factorization axioms, we can factorize this map as a cofibration followed by an acyclic fibration. Well, there's the other factorization as well, a cyclic cofibration followed by a fibration, but we don't need it yet. We will need it for fibrant replacements or models. So since this arrow is a cofibration, by definition, C is cofibrant or cofibrant, and the second arrow is a weak equivalent. So in the localized category, C and X are isomorphic. Similarly, similarly, we construct fibrant replacements or fibrant replacements. Let me just put it in this way. C intersected W. So this the first arrow is an acyclic cofibration, the second arrow is a fibration, which means Fx is fibrant. Okay, so now we know what a cofibrant replacement is, and we just simply apply L to it, and then take the class in the localized category. Well, similarly for the other functor, but we need to take the fibrant replacement instead of the cofibrant replacement. Does this make sense? So far, I've just said something about objects. I didn't say anything about morphisms. And but the idea for morphisms is exactly the same. Okay. Now we want to calculate the unit of the adjunction in our case. But we want to calculate the derived version of the unit, so we need to be careful. So we start with the simplicial set K. K is already cofibrant. So we don't need to do anything. We just take APL so the APL of K already gives one the right answer. And then, unfortunately, in CDJ op, as opposed to CDJ itself, not all objects are fibrant. So we need to take a fibrant resolution in CDJ op, or which is the same, a cofibrant resolution in CDJ. Well, usually. if K is empty, then it's probably fibrin, but in all interesting examples it isn't. So what do? We take we take a Sullivan model, lambda V APL of K. Well, to be more precise, we have some differential here, which we will not need except to know it's there. Okay, Sullivan model. Okay, so this gives me a fibrant replacement for APL of K in theta J op. And then so let me say that this is and then I use I apply the right adjoint functor. And I get APL of K, geometric realization, goes to lambda V, because the functor is contravariant. Then so these are spaces. And then I have the usual unit. Which I precompose with this arrow. And the resulting thing will be the derived unit. Meaning the arrow which represents the unit in the homotypic category. In particular, if I prove that this derived unit is a weak equivalence, then K is in this category, which is equivalent to this category. So I want to know for which simplicial sets the composite map is an equivalence. Well, let's let's see. I want to show that this map is a weak equivalence for let's say simply connected spaces or abelian spaces, sufficiently nice spaces. Well, to do this, I need to remember what the right and left adjoint functors preserve. Well, we all know that the left adjoint functors preserves what? Limits or colimits? Colimits. Okay, well, similarly, the right adjoint functor preserves limits, but in our case, it turns out that the left adjoint functor also preserves some colimits. No, some limits. So let's write this down. APL preserves colimits. The geometric realization preserves limits, but APL also preserves some limits too. And here is the biggest ingredient which I will be using as a black box. So the statement I would like to use is the is a version of the Adlenberg-Moore theorem. Suppose I have a diagram of some visual sets such that well, let's say Z, Y are fibrant. X to Y is a vibration. Then then APL takes the limb of the diagram to the whole limb of the image diagram. Okay, now do we want to know what on earth this means? Or do we want to finish now and discuss it briefly later? Well, later meaning probably next week. Так, значит, хорошего понемножку, Саша, я правильно понимаю? Хорошо. Хорошо, тогда, so there's this theorem, but we have this homotopy limit, and it's not exactly clear what this means. So this needs to be explained, and also where these strange requirements come from. Well, basically, these requirements guarantee that the limit of this diagram is the homotopy limit. So, in other words, in our case, APL takes the homotopy limits of the diagrams of this type to homotopy limits. So, APL preserves the homotopy limits of the diagrams of a very simple type, namely of this type. Are there any questions? Окей. Так, значит, тогда в следующий раз, ну, видимо, do we want to finish the sketch of the proof? Good. So probably in this case, next time I will try to finish the proof. Well, I think the first half of the seminar should suffice, and then probably you will start talking about model structures, and which means probably your talk will be in 2 weeks. Okay? Any more questions? Remarks? Well, this is it then.